Yes, yeah, good. So,
It is recording. All right. Not bad. All right. So so now we're going to look at some cases. So we're going to do a case where Z, the point above the sphere, is greater than R. Okay. So because we have these absolute values in the integral. Okay. I don't care about you, go away. All right. So if Z is greater than R, then Z minus R, absolute value is just Z minus R, right? And Z plus R, that's easy. That's just Z plus R. Yeah. Okay, so then our Z minus R, this little business up here, this is Z minus R over Z minus R, right? Plus Z plus R over Z plus R, and that's just 2, right? So we end up with EZ component, the Z component, right? Which up here, you can see this actually should have a Z hat because this is the direction of E, right? Z hat up there, by the way, because that's the whole vector E. So if I just want the Z component, I'm just going to take the stuff in front of the Z hat, okay? Is K, which is 1 over 4 pi epsilon naught, and then it's 4 pi R squared sigma over Z squared. Now this here, this 4 pi R squared sigma, 4 pi R squared is the total surface area of the sphere. Sigma is this surface charge density. So those two things multiplied together is just the total Q on the sphere, right? So this becomes 1 over 4 pi epsilon naught, and then Q over Z squared, which looks a lot like the field you would get from a point charge at the origin, right? Does that make sense? Okay. All right, what about inside the sphere where Z, case Z less than R, then Z minus R, absolute value is R minus Z. And so we get, and then Z plus R is the same, it's just Z plus R. So we get we get this stuff up here, right? It's going to be Z minus R over, gosh, I cannot read my writing, minus Z minus R. Sorry, not absolute value, just parentheses. And then the Z plus R over Z plus R, that's just 1. And so this becomes -1 plus 1, which is 0. So EZ inside is equal to 0. Okay. All right. So this is a sphere of charge, right? And outside it looks like a point charge with total Q, right? Inside the field is 0. So this hints at a better way of doing this, which is how we're leading into the divergence and curl of E, which is our current section, which I forgot, 2.2, I believe. Maybe 2.3, I can't remember. 2.2, 2.2. Okay. All right, so let's go on to that because see a much easier way of calculating something like that because that was kind of ridiculous. Okay. All right, so we're on to section 2.2, and this is the divergence and curl of E. Okay. All right, let's talk about field lines first. Okay. So field lines, if you all know what those look like, we'll just be a little bit more specific here. For a point charge, right? They, let's say this is a positive charge. They just go radially outwards. Right now, let me move that plus here. I know this is really bad drawing of radial. So these are meant to indicate the direction of the electric field, right? But if you think about what a point charge electric field actually looks like, right? It would be like big vectors pointing out later because the field's strong there, and then a little bit shorter later, and then a little bit shorter later, and a little bit shorter, meaning like the field's getting less strong, but it's pointing radially out. So people don't, it's annoying to draw those, they draw field lines, right? And the density of the lines tells you how strong something is. Okay, so if I was really good at drawing this, which I'm not, right, then I would draw like dense lines here. And you can see as they fan out, they get less dense, which is how we represent the field getting weaker, right, as we move away from the point charge. Does this make sense? Because they're fanning out radially, so as you go out, they're less dense. So that's really how lines are supposed to be drawn. Terrible drawing, but and field lines, they start on positive charges and there doesn't need to be a comma there, sorry, and end on negative charges. Okay. All right. So if I were going to draw, you know, field lines for plus charge, negative charge, right? The field lines would come off of the plus charge and end on the negative charge. Right? And the direction of the field is the direction in which a positive test charge would be pushed. Right? Does that make sense? Yeah. Okay. So a negative test, this even though it looks like those lines are pushing the negative charge away, the field, the force on a negative charge would be attractive, right? Because you would multiply the field E by negative Q. Let's say this was Q and this was Q, but this was negative Q, plus Q and negative Q. Okay, does this make sense, sort of? And then, you know, there's lines coming off this way too, and they're heading for the negative charge. And there's lines, those lines would be connected up and they would come in here. Okay, yeah, all right, just, okay. In this model, field lines, the flux through a spherical surface, right, would be, we write it as big phi E, which means the flux due to the, of electric field, and it's defined as the integral, surface integral of E dot dA, right? Okay, you've seen that, and it's a measure of the number of field lines that pass through S. Okay, so this is a measure number of field lines okay. All right. Now remember, when we draw field lines, we're really not drawing all the, you know, I mean, the electric field permeates all of space, right, near the charge and dissipates as you go away. So we're not drawing infinitely many lines, right? We're just drawing a few of them, right? So your flux is never infinite, right? But so it seems like should be, you know, it seems like it should be infinite if you really were drawing all the lines that exist, right? But we're not. We are sampling lines, and that's how you should think about the flux. Okay. And remember here that the dot product, this E dot dA, is picking out the component of the lines that are perpendicular to this outward pointing normal, right? That's because on a surface, so if we had our S here, let's make this guy in yellow. So if I had like a surface like this, dA would point perpendicular to the surface, right? And you might have field lines that are coming in like, you know, like this or something. And then you'd have a dot product between the two and you'd pick out the component of E, right? That's along the lines. Okay. Okay. So because we know that the number of field lines that we draw around a charge is proportional to how big the charge is, right? If this guy here, if I all of a sudden made it 2Q, right, I'd have to fill in like more, double the lines in here, right? If this was 2Q, right, I'd have to fill in double the lines, right? Because this density of lines is proportional to the strength of the charge. So that means that the flux through the closed surface must be some measure of the total charge somehow, right? Yeah. All right. And that indeed is true. Yeah. So if you have a positive charge inside a closed surface, right, all of those lines are coming out and they end on some negative charge that's outside. Maybe there's a little negative charge that's in there. Let's think about the case where you have a 2 plus 2Q inside and a negative Q inside as well. Well, half of the lines from the plus 2Q will end on that negative Q that's inside, but the rest are going to go out and end on some other, who knows? Think of a negative charge at infinity or something, right? So it's a measure of the net charge really inside the surface, isn't it? Because you could have other charges inside. If they don't match up perfectly, all the lines won't end on the negative charge, right? To cancel out all the positive charges. Okay, so this is really Gauss's law, that this is proportional. So we're going to make this a little bit more formal. Let me get another layer. All right, so we have the integral around a closed surface S of E dot dA. And let's just look at we're not writing Gauss's law down yet. We're just looking at, let's just let this be a sphere of radius R, okay? So we'll let the S be, let's go, let S be sphere of radius little r. Okay, so we'll have a point charge inside. Okay, all right, fine. So we can do this integral really, right? So we can say, okay, this is the integral of our S E dot dA. We have the integral E. So E in this case is going to be K Q R hat over R squared, right? The computer's doing its thing again. And then we have to dot that with dA. In this case, right, this is a sphere. So remember what dA vector is going to be, right? We are not changing R because we are just going on the surface of that sphere. So this is going to be R squared dl theta dl phi, and it's going to be in the R hat direction because the R hat direction is perpendicular to the surface. Yeah. Okay. So this is going to be R squared sine theta d theta d phi in the R hat direction. So we have R squared sine theta d phi in the R hat direction. So the dot product just gets rid of those two R hats, right? And we end up with the integral. And now I'll kill that little symbol that goes around because we're writing out everything. And let me pull out some stuff. So we're going to have K and we're going to have Q. And notice the R squareds cancel out. And then we have the integral of sine theta d theta and the integral of d phi. And we talked about how this goes from 0 to pi and this goes 0 to 2 pi, and that this integral is always 4 pi. Yeah. Yeah. Okay. So what does this end up being? K Q over 4 pi. Oh, not over 4 pi. Hello. Times 4 pi. All right. But K is 1 over 4 pi epsilon naught times, then we have a Q and then we have a 4 pi. or pi's go away, and we get q over epsilon naught. Okay, and this ends up being true no matter what the surface is. So this, you can see the r squared canceled out. It doesn't matter how big I took the sphere, right? Yeah, in fact, it doesn't matter what kind of surface it is. So I could have surrounded that point charge with some wacky looking surface, and this integral would end up being the same. Okay, I'm not going to prove that, but that's Gauss's law. So Gauss's law, if we write it up here now, is that the integral around a closed surface of E dot dA is equal to the Q net over epsilon naught. Right, Q enclosed. I guess I should say more like Q enclosed, because you will calculate the net by figuring out what's enclosed, right? Because there might be like 2Q minus Q, and the net would be Q, but those all have to be enclosed. Again, I'm not going to prove that. All right. And it's also the flux through the surface. So the total flux through the surface is just the Q over epsilon naught for any surface. All right. This is the integral form of Gauss's law. There is a differential form of Gauss's law that we can get there by using the divergence theorem. Okay, so let's get another layer. All right, okay, so let's look at the differential form. So we start with divergence theorem. And that is if you have a integral around a closed surface of, a field dot dA, that's equal to the integral of the volume enclosed by that surface of the divergence of that field, integrated over all volume. Oh, sorry, over the volume enclosed by the surface. So in the example with that was a sphere where S was a spherical surface, the volume, of course, would be inside the sphere, right? And you're integrating over the spherical volume inside. Okay, now we can also write, so this is divergence theorem. I haven't done anything really, but just write that down. But I want to point out that in the total Q, so I'm going to write it big Q. So we could probably just go up here and change this to big Q because that's kind of what the book uses. So we'll do that. Big Q. This is meant to be Q enclosed. All right, so Q enclosed can be written as an integral as well, because it's the integral over the volume of the volume charge density d tau, right? Yeah, this is what we said before. So we can, we know that this guy here, so we know that here, this part is Q enclosed over epsilon naught, right? So that means that this part that I can write now, this as 1 over epsilon naught integral rho d tau over volume. And notice now that I have two integrals over the same volume. And right, that means that, and I can put this little epsilon, I'm going to put this little epsilon inside the integral. There we go, just because it looks nicer. And so that means that the integrands between this guy and this guy have to be the same. So I can write del dot E is equal to rho over epsilon naught. And this is the differential form of Gauss's law. Okay, this is the integral form up here, right? Integral form. Okay, this is one of down here, this is one of Maxwell's equations. Well, they're either forms, because there are integral form of Maxwell's equations and differential form of Maxwell's equations. This is the first Maxwell equation that we've seen. Okay, it's often the first that gets introduced. I mean, you've seen this version in 116, right? Integral form. Yeah, probably didn't see the differential form. Okay, but it is one of Maxwell's equations. Okay, let me get to my next fact. Yes. All right. Okay. So let's calculate the divergence of E. Okay. And we'll do it for a general E, not for a point charge, but just for a general E. So let's do this part here. All right. Calculate. Now, we just proved this equation, not proved this equation. We used what we knew about the integral form to get the differential form, but we use this, right, for the spherical surface. I said it's good for everything, but let's be a little more general when we calculate the divergence of E and see if it's true for just any old E. Okay, right. So, okay, so let's do that. So we're going to write a really general form of E. Right? This is the most general form you can write down for E. That is 1 over 4 pi epsilon naught, and then the integral over volume of rho, the surface charge density, which in general would be a function of r prime. Remember, r prime points to all the pieces where, all the places, right? So you might have some weird volume. R prime points out to a little chunk over here, and the charge density there, the volume charge density might be different there than it is at a different R prime, and a different R prime, right? Rho doesn't have to be constant. Okay. So it's rho of R prime, omega hat over omega squared. This is super general, right? This works, and this is d tau prime. Remember, we're always integrating over the prime, right? Because we're moving our prime around to point at all the different sources of charge, and we're integrating that up, right? Okay, fine. So we can actually just change this integral to not just be over the volume, say you have some blob and it's got all kinds of different charge densities if you look at all the different places inside the blob. But in our assumption here, we're calculating E to that blob, and that's all there is in the whole universe is that blob, right? We're not like, let's have that blob, but then over there's another charge density and blobby thing. No, it's like, that's all there is. This is our example, right? If there was a blobby over there with more charge density, then you would incorporate it as well into this integral, right? So outside of this, whatever we're integrating over, there's nothing. So there's no reason we can't extend this integral to all space instead of just over the volume of the blob, right? You understand what I'm saying? Okay. So we're going to say, all right, 4 pi epsilon naught integral all space. And the same stuff, right? It's just saying I want to change the limits. Omega hat, d tau prime over omega squared. Okay, good. All right. Let's take the divergence now of this thing. Okay. So we're going to take del dot E. Okay. So we're going to take del of this integral. Now let's be careful, right? Remember that here, del is taking derivatives, right? As we know, it's not taking derivatives with respect to the prime coordinates, because those are right. Think about, look at E. E doesn't have any prime coordinates left. Once you do the integral, there are no prime coordinates left, right? Because you just integrated over those as you pointed to all the pieces, all the little dq's in the blob, right? You pointed all those, you integrated it up. There are no primes left. It's just unprimed, right? X, Y, Z, R, theta, phi, whatever your coordinate system is. E only depends on R. So the derivatives are only depend on on the unprimed coordinates. Does it make sense to you? Yeah. So I can actually bring that del into the integral because I am integrating with respect to prime coordinates, not unprimed. Okay, so I'm going to have 1 over 4 pi epsilon naught. The integral, I'll drop all space, but that's implied. And then del dot. And then what are the vector components of this? Well, it's just omega hat, but I'm going to write it as omega hat over omega squared and rho of r prime. Now that del is taking the derivative of, well, okay, let's think it through. 1, the vector quantity here is the omega hat. The only unprimed coordinates that exist inside the integral are in omega hat and omega squared, right? Because rho only depends on r prime. So the derivative of that stuff is 0, according if you're taking the derivative with respect to unprimed coordinates. Okay, so the derivative is really only being applied here. Okay, by product rule, I have already said del acting on this is 0, right? Okay, all right, so that's that, and we've seen what that is, right? We have actually written that down before when we looked at direct delta functions, and that was that this was 4 pi d3 omega, okay? So I can replace that. I get 1 over 4 pi epsilon naught. And then I get the integral of 4 pi d3 omega rho of r prime d tau prime. Okay. I said this integral was of over all space, right? So this should be pretty easy to write down. And instead of omega, I'm going to write it as r minus r prime, right? Because that's what omega is. All right. So I'll write it one more time. We have, I'll bring the 4 pi's out. We'll cancel those guys. We have 1 over epsilon naught. We have the integral of d3 r minus r prime, right? And we have rho of r prime d tau prime. Well, this just gives me, according to delta function, how delta functions work, rho of r, right? Collapses that integral right away. Okay, so what have we just gotten? We've just gotten that del dot E equals 1 over epsilon naught rho of r, right? This is we just proved Gauss's law again for the most general E that could ever exist, right? So it is true for any E. It's just now rho could depend on r. We didn't write that down before, right? Okay. Where did I just put this? Okay. So you've all used Gauss's law many times in 116. What did you use it for? Do you remember?
Finding electric fluxes.
Okay, finding electric fluxes. What else? You used it a lot less for getting the flux than for getting this other thing. Used it over and over and over to get a very particular thing.
To get the charging clothes.
No. Yes. Used it to get the electric field like a billion times. Yeah. Okay. You may not remember it. Yeah. But it's what you end up using it for. And I think that causes a lot of confusion because students think that's what that's what it's for, right? And somehow you can always get E, but that's not true. You can't always get E, and we're gonna talk about that. So let's get an example where you can get E, and we're gonna go back, right, to our, let's see if I can find my, there, to this guy. And I'll go back to one where it doesn't have anything on it. There we go. We're gonna go back to this problem. Okay. It's got a surface charge. Sigma, which is constant over the whole sphere. Okay. Let's use Gauss's law in integral form. To get our field at Z. Okay. All right. Okay, so let's just think about the surface. What would be a good surface to take here? And the goal is to get a surface where E is constant everywhere on that surface. That's your goal when you have a Gauss's law problem. We're going to try to get the E out of it. What kind of surface do we think we can make so that E is constant everywhere on that surface?
Is it uniform charge?
It would be a sphere, yeah. And if we want E at Z, what would be a good idea for the radius of that sphere? Yeah, to be Z, absolutely, yeah. Yeah, so let's take a sphere, so take S sphere of radius Z. Okay. All right, now, in what direction does it point everywhere on that sphere, the surface of the S sphere?
Radially out.
Radially outward, absolutely. In what direction does DA point?
Radially out.
Radially outward, exactly. So E dot DA for our surface, right? So if we were going to draw DA, and I don't want to draw it in yellow there because it's going to be, see it, but it'd be radially outward, right? Okay, so E dot DA is just going to be, sorry, it's got to be yellow, EDA, right? Because it would be E times DA times the cosine of the angle between them, the cosine of the zero, yeah, there's one, okay. Okay, so EDA, okay, perfect. Fine, so if I look at my integral side up here, so if I say the integral S of E dot dA becomes the integral over S of E dA, but we just said it's constant, and so E can come out of the integral, and it's the integral over that surface of just dA, and that's going to be E is now times the surface area of my sphere radius Z, right? Surface, right? That's what the dA adds up to, right? Okay. Now you could write out dA if you would like to. So let's just as an aside, you could write it out. You could say, oh, this is Z squared, right? Sine theta, D theta, D phi, if you like. It's just faster to be like, well, that's going to add to the surface area of that sphere. But, you know, let's be a little pedantic about it. So then we have E, Z squared is constant. And then we'd have integral sine theta, D theta, integral D phi, 0 to pi, 0 to 2 pi. And again, this is always 4 pi. And so we get E times 4 pi Z squared, which indeed is the surface area of the surface, right, of S. Okay, so that's on one side. Now the Q enclosed, right? So we need Q enclosed now. So Q enclosed over epsilon naught. Well, we know that's the integral of the surface charge density, which is a constant, right, times dA. Okay, well, we know what dA is. So this is going to be, now we have to be careful here because this is the surface of the sphere, not our Gaussian surface, right? It's the surface of the sphere. Okay, so that's going to be sigma times 4 pi r squared. Yeah, over epsilon naught. Okay. Yeah. Okay. And if I just wanted to write that as the total Q, I could, but all right. So now I have these two together, so I have the pink, which is E is 4 times 4 pi Z squared is equal to sigma times 4 pi R squared over epsilon naught. I can cancel out these 4 pi's if I want, and I get E is sigma R squared over Z squared epsilon naught. Now, this is exactly the same thing. We just wrote it as Q before. We wrote it as Q over Z squared, which we could have done, right? Okay, let me be a little more clear. I'm gonna come up here. Let me erase some of this. Let's come up here. All right. So we have E times 4 pi Z squared. And on this side, this is the total charge Q equal Q over epsilon naught. Yeah. So E, the magnitude of E is Q over 4 pi epsilon naught 1 over Z squared, just like we had before with the other method. It's exactly the same outside of the sphere, outside of the sphere. And if we want to put a vector on it, we know already that it's in the Z hat direction, right? Okay. Okay, what about inside the sphere? Well, inside the sphere, we can make a surface inside the sphere, right? We can make a surface inside the sphere of radius little r. Okay. And the integral of the E on that surface is also constant, right? It's also, if there's any E at all, point straight out, okay, just by symmetry. But the other side of the equation is where we should concentrate, right? Because it says Q enclosed, but there's no Q enclosed. So that's 0, which means the field is 0, right? Yeah, okay. So same exact result as we got before. Here, using Gauss's law for getting E is that you cannot do this unless E is constant everywhere on your surface, so you can pull it out of the integral. Otherwise, you've got nothing. You can calculate the flux all day long. That's fine, because you don't have to take E out of the integral for that. You could, as long as you can do the integral, you can calculate the flux, which will get you the total charge, right? But you can't get E. You want to get E, it has to be a problem that has the symmetry that allows you to pull E out of the integral. Okay, but you could always calculate the flux as long as you know what E is. You could always calculate the flux, right? Just gotta, might be a nasty integral, but you can do it. Maybe with a computer, but yeah. Okay, so and actually, you don't really care. You don't really have to do it with a computer because if you know the total charge. So if that's something you know, then you know the flux already. If you know the total charge inside that surface, you know the flux. You don't even have to do an integral. It's just Q enclosed over epsilon naught. Okay, so let's look at, let's time it is for one thing. Okay. So let's look at, if we do, so let's say that we were doing the problem previous to that, or let's do another problem, sort of. So let's say we have a sphere, like a solid sphere of charge, okay? And now I can easily calculate the field with this solid sphere, from the solid sphere of charge, using Gauss's law, as long as I choose a spherical surface to be the surface, right, that I'm interested in. But if I told you, hey, don't do that, I want you to calculate the flux through, there's a box surface, okay? You could no longer calculate E with this, right? You can't do that. But you can tell me the flux, because all you have to do is figure out what the total charge is. And if I gave you rho, you just say, oh yeah, the flux through our square, or cube, sorry, is Q enclosed over epsilon naught. And I just go, oh yeah, well, I have a rho, so integral of rho dV over the volume of the sphere over epsilon naught is the flux. And if it's constant rho, that's easy. It's 4 pi, let's say this is r, 4 pi r cubed over 3 times rho over epsilon naught. And there you go. Right? So it doesn't even matter what that surface is. If you're just getting the flux, all you need is the total charge. Now, if rho is some complicated function of r theta phi, then you might have a hard time doing the integral to get the charge. Right? But if it's constant, it's very easy. Does this make sense? So no matter what that surface looks like, you can get the flux. You might have to do a yucky integral to get the charge, but you can get the flux. Okay. Let's do an example. Yeah, and there may be a video for you to watch. We'll see how far we get today. Yeah, they're already up though. So there may be extra you can watch again, or stuff that's going to fill in the rest of this section of the lecture. Okay. All right. So I'm gonna get a new layer to do this example. So now we're gonna start doing a few examples where we do have the symmetry. So spherical symmetry, you're good. Cylindrical symmetry, you're good. Planar symmetry, you're good. Anything else, not good. Okay. All right, so meaning you can get the field, right? So that's what we're gonna try to do. So we'll do an example here where we have a long cylinder which carries a charge density rho is equal to Ks. So S here is the radius, so is a variable that tells you how far from the center of the cylinder you are. Okay, so we're going to be in cylindrical coordinates, where S is that, so if I were drawing in 2D, this would be S, right? And this is the center of the cylinder. Yeah, this is X and Y. And then Z goes along the length of the cylinder. Okay, so this is not a constant charge density, right? It's not. Okay. We want to know what is the electric field inside. Okay. Well, let's do a little drawing here. So we'll have, this is the Z axis, and we have a cylinder. This is the physical cylinder in blue, so the actual cylinder. Okay. And if we were going to draw S here, S would look like this, right? This would be like S. Okay, the variable S. And as S sweeps around, that's phi. So I'll put that here, phi, like this. Okay. So phi goes around 0 to 2 pi. Okay, now, if we want a Gaussian surface to use to get L, right? Get L. To get E, what kind of surface should I use? What shape? Cylinder, yeah. You try to use a sphere, is that gonna work? Yeah. Okay, try to use a square or a cube. No. Try. It's not gonna work. Okay. Yeah, you want something where the field is going to be constant. Now, it may not be obvious at all that the field's constant here, but think about the charge density is growing, right? And that K, by the way, is a different K. So this is not equal to 1 over 4 pi epsilon naught. So bad notation. Maybe we should use C. There we go. Some constant. So the charge density is growing as you move along S in the cylinder, right? But there's nothing here that tells me that, if I move around in phi, that it changes, right? So if it moved around in phi, then the direction of the electric field might be weird, right? In some weird direction. But because it's all sort of radially symmetric, the field should be pointing in the same direction and constant at a particular S. right? Okay, so let's go make a surface. And so we'll have yellow be our surface here. And so we're gonna make a little guy inside because we're interested in the field inside. Okay, and this of course is S along here, and we'll have its radius be S because that's where we're interested in. We were inside somewhere at some S, and we'll have it be L long. We won't care what L is later, you'll see. Okay, so first thing is, let's just write down Gauss's law. And that's going to be the integral of S E dot dA is Q enclosed over epsilon naught. Okay, so first things first, let's just get Q enclosed, okay? Because just the fact that that rho is not constant means that we got to do teeny bit of work to get it. Okay, so I know that Q enclosed, so let's do that in this blue. So Q enclosed over epsilon naught. We know that we've got to do the integral of rho d tau prime, okay? And so this is the integral of C S prime, right? Because now we're in prime coordinates. And then we need d tau prime in cylindrical polar, okay? So we said this back when we did cylindrical polar, but that is S prime ds d phi dz. Okay, that is d tau prime, d phi prime dz prime. Okay, all right. And so this is the integral up at the C outside, the integral over S prime squared ds prime from 0 to S, right? We're integrating we're inside our Gaussian sphere, Gaussian surface, right? And then the integral 0 to 2 pi d phi prime integral 0 to L dz prime, right? Okay, let's do those integrals. So we have C, then we have S prime cubed over 3, then we have 2 pi, then we have L, okay? So all together, I'll write it a little differently. C 2 pi L S prime cubed, oh, sorry, S cubed. This is prime, but I'm applying my limits real fast. I hope that's okay. S cubed over 3. You good with that? Yeah, okay. So we have the charge enclosed over epsilon naught. Okay, that's good. All right. So we already said that in our Gaussian surface that E is going to be pointing radially outward. We said it's going to be constant on the surface, which means I'm going to be able to pull it out in the integral. It also means that E dot dA is going to be E dA, right? Because E's pointing radial out and dA is in the S direction as well, right? So this integral now, this part, is going to be the integral E dot dA is just going to be E integral dA. And again, we said that oh, and I better be a little careful here. So yeah, let's back up just a tiny bit. So the integral over the closed surface, so let's get rid of this for a minute. I think a little bit, because this is a closed surface. It's not just the cylindrical surface, it's the caps as well, right? So we know that the integral over the closed surface E dot dA is going to be the integral over the cylindrical part of E dot dA plus 2 times an integral over one of the caps, right? A cap of E dot dA. Okay, let's look a little closer at a cap. So we had a cap like this, dA is going to point outwards like this. So let's say this is the rightmost cap. And E though is gonna be pointing like this. So what's E dot dA? 0. So we don't care about that. Okay. Okay, so we just have to worry about the cylindrical part, which we already said, hey, that's easy because E is constant there. E dot dA is just EDA. Okay, so I'll keep going with that. I'm gonna erase this little thing here. So we have E, and then the integral dA, which is now just the surface area of our cylinder, right? Not including the cap. And that's just 2 pi SL, right? So this is just going to be E times 2 pi SL. Okay, now we can put it all together, right? So we have the pink and the blue put together. I'm going to come up here. All right, so we have E times 2 pi L on one side, and on the other side, and I think I left my epsilon not off everywhere, my bad. So let me go put it back in. There we go. Okay, so on this side, we have C times 2 pi L S cubed over 3, and then we have 1 over epsilon naught. The L's go away, the 2 pi's go away, and we get E is equal to C over epsilon naught S. Oh, I left an S out. Sorry. Thank you. I heard someone say something. Yeah. Okay, so one of those S's cancels this guy. So we get S C over epsilon naught S squared over 3. Yeah. And then we can put the vector sign over it and say this is in the S hat direction. Right? And notice it depends on S, which it should. Yeah. Okay, this is we did spherical symmetry, cylindrical symmetry. Now let's do planar symmetry. Pretty much the only 3 things you got to get the field out of, right? Okay. All right, let's do an example. An infinite plane. With uniform surface charge. Sigma. What is E above plane? Okay. All right. So let's just kind of do a side view of our plane here. Okay, we'll do a side view. Here's the plane. Now it's an infinite plane, so we're never going to be close to the edge. Edges are an issue, right? If you had surface charge on and you just had a plane the shape of this size of this table near the edges, E is not going to be pointing straight up, but I can pretty much guarantee you it's going to be pointing straight up if you're really far from the edges, and you're always going to be far from the edges, right? Okay, if it's infinite. Okay, so this is the side view. And so E is going to point up on this side and down on this side. Okay, it's a infinitely thin plane, so it's not like this chunky table. Okay, okay. All right. So to use Gauss's law to get this, we use what's called a Gaussian pillbox. Okay. Use Gaussian pillbox as our surface. And that's a pretty easy thing to visualize because it really does look like just a little box. Okay, so it's like you have a box. Sometimes people draw it as like a little cylindrical box, but it's kind of spans the plane like this, right? It's above and below the plane. This is our Gaussian pillbox. Okay. Okay, and the Q enclosed in our Gaussian pillbox is just gonna be the sigma times the area of the top of the pillbox, right? Area, this is area of top of pillbox, right? Yeah, because you're kind of like stamping out. You have an area, like imagine it's a cylindrical pillbox. It's kind of just stamping out amount sigma, right? Because of its area is A. Does that make sense to you? Okay. All right. And so now we just need to get that integral E dot dA. Okay. So let's get integral E dot dA. Okay. So let's think about it. We have the top of the pillbox and then the bottom of the pillbox. And we have the sides of the pillbox. But on the sides of the pillbox, dA points outward and E dot dA will be 0. So it's only the top of the pillbox and the bottom of the pillbox that I have to integrate over, right? So I know that for the top surface, so this is the top E dot dA plus the integral of the bottom E dot dA. Or little dA, whatever, big dA. Okay. Okay. All right. Well, the top surface, let's do that one. So let's go down here. Integral top surface is going to be I can pull E out, E dot dA, they're both in the same direction, right? I can pull E out because by symmetry, it's all constant, the whole everywhere on that, okay? And so I just get E times A because integral dA is just A. Okay, for the bottom, integral E dot dA. Well, E points in the opposite direction, dA points in the same direction, and this again is EA. So these two things add together equal to EA. So putting it all, Gauss's law, put it all together now, right? We have 2EA is equal to sigma A. Notice the A's cancel out. We don't care what the A is. Epsilon. Yeah, well, I didn't put it over here. I should have put it over here because I like to keep it hanging around so I don't forget, and I always forget it. Okay, so that means that E is equal to sigma over 2 epsilon naught. And we want to put the vector nature in, we're going to use n hat, where n hat is just a vector that's perpendicular to the plane, right? And also points down here too. So whatever surface you're looking at, that's the direction. Okay. And I want you to notice, this is a really interesting property here. Now it has a function of the fact that it's infinite, is that it doesn't matter how far away from the plane you are. Right? Yeah. Okay. Let's use this fact to do another problem. Okay, so we're going to do another planar problem. So we're going to have two infinite parallel planes. We have two planes. We'll look at a side view of them here. And they are next to each other. Okay, and we're going to find the field. We want to find the field. They both have sigma. Oh, no, sorry, that's not true. They have, one of them has sigma and one of them has negative sigma. Sigma, and the other one has negative sigma, the opposite charge. Okay, so we want to find the field in three regions. One to the left, of both 2 between them and 3 to the right. Right of both. So let's label those regions. So I have region 1, I should probably color code these, so I think I'll do that. So we're gonna do region 1 in red. So region 1 is to the left of both. And region 2, doing blue, light darker blue, okay, is between them. And then region 3, I guess an orange. I don't know if you can tell the color differences there. I think you can, maybe. Okay. There. Oh, right. So we can draw the fields in there, right? Remember, we know what the field is. And remember, because of superposition, if we want to know what the field is for the yellow plane, we don't care that there's a pink plane there at all. Okay. So I can draw the field due to the positive charge guy. So let's draw that. I'll draw that in yellow. So the E plus is going to look like this, right? And it's going to look like this on this side. And the magnitude of those E's are the same, right? Remember, that does not change. So if I go over to the pink plane, I'm going to have the same E plus there, right? So E plus here's the same exact size as it was over there. Yeah? Okay. And for the negative plane, for the pink plane, I know it's going to be the opposite direction. So if I were going to draw that, I would draw it going into the plane, right? And then here I got to draw it going in the same direction. Oh, wait, my bad. Opposite direction. Opposite direction coming in, right? And then over here, also coming in. Does this make sense? But all the same length. So now I just need to add up stuff. Okay, let's look at region 1. Region 1, all the vectors cancel. The yellow cancels the pink. So E is 0 for region 1. Okay. For region 2, they look like they add. They're in the same direction, right? Don't they? Okay, so we have region 2. We're going to have E is equal to, what was it again? It was 2. Go back and look. 2. Oh, no, it was sigma over 2 epsilon naught. And then, and they're both in the same direction, plus another sigma over 2 epsilon naught, which just gives me sigma over epsilon naught. And these were in the n hat direct, or, in the, to the right. So I have to say to the right. Because I can't really define a vector unless I define a coordinate system, which I could, right? If we wanted to, we could define a coordinate system where we would say, like, let's say this is plus x and this is negative x. So this would be in the x hat direction. Right? Yeah, we could do that if we like. And then in region 3, they cancel again, right? Don't they? And so for region 3. Yeah. All right. Well, I think we'll quit there. There is a video that you can watch on the curl. Okay, so one of the videos says a curl. Well, just look for it. There's a few videos there. You'll find it. It'll be easy to find. All right. And let me shut the Zoom down. Stop share. And then I need to stop recording.